I most of my talks fall into one of five categories, and these are kind of key areas I think that hams should have some knowledge of, and you can keep building your knowledge in these areas. You know, operation of radio equipment and power sources, operating protocols, whether it's nets or contesting or emergency communication, whatever it may be. Propagation and band mode selection, that kind of fits in here. Selecting and installing antennas and feed lines, and then troubleshooting and resolving equipment failures. All those areas are, I think, useful areas of study for any ham, and you can build up your skill to be very considerable in any or all of these areas. So we're going to talk basically looking at getting a signal from one place to another. First, VHF and UHF. And then we're going to take a look at microwaves, which are similar, but they've got some other interesting features there. And then we'll finish up with shortwave, all the HF stuff. And as the slide says, each of these segments and groups of bands has a number of different mechanisms for moving RF from one place to another. So we start with VHF and UHF. They're pretty similar. You've got line of sight plus a little bit further, and that basically, if you were to, I'll show you a chart in a minute, but if you were to stand at a certain height, if the Earth were a third bigger than it actually is, in other words, a little bit less curved, that's how far the RF would go. So it's a little further than you can actually see the visual line of sight. That's called 4/3 Earth. But line of sight, as is predicted by topo map programs and Google Earth and things like that, those are the kinds of things that will at least give you a pretty good picture of where a signal might land on VHF and UHF, what's in the way, and that sort of thing. In addition to line of sight, you've got reflections and diffraction. You can knife edge over mountains, and reflections. We're just talking about basically bouncing off, buildings, mountains. If you've ever driven around in an urban environment on a VHF or UHF repeater, and you're talking to somebody, and you hear some flutter, often that's basically different reflections off various buildings and so on that are either adding or subtracting from one another. So that's where you get some of that variation in signal strength, and even some a little bit of interference from one to the other. Tropospheric ducting is a different. This is like the lowest layer of the atmosphere, and what happens is you get a layer that has either temperature and moisture differential, and it can form pretty much like a almost like a waveguide that kind of follows the curve of the Earth. And tropospheric ducting is a feature that usually pops up in a big way in Southern California once every summer. It's been getting a lot shorter lately, but we used to have up to a week where stations at the appropriate elevation on the West Coast would hear signals in Hawaii. The Hawaii end is fairly high. There's a repeater up there, and there have been cases of people down in the South Beach area actually just working people on Hawaiian repeaters. I myself have managed to contact a friend when he was over in Hawaii on 2-meter sideband, and I heard the 432 beacon there, but we were not able to complete. This was kind of tail end of the duct opening. If you ever want to see how what can be done there, there's some articles in QST. Look for Wayne Overbeck, November 6, November Bravo. Wayne went some years ago over to Hawaii equipped with gear that he put on a rental car, and set new world distance records for I think 900, 1200, 2 gigs, and 3 gigs. And they almost did 5 gigs, except, and he heard the LA, the California station on 5 gigs quite clearly, but the station here had so much interference from consumer Wi-Fi up on 5 gigs that he could not hear Wayne back. So that record still belongs to Chip Angle in 6CA, who did that decades ago. But tropospheric ducting can also be shorter. It can run typically along the coast. Um, and East Coast tends to have an awful lot of this, maybe just because the moisture is greater. We're a little more of a desert. But the East Coast, you can see, look at the tropo maps and see all sorts of paths up and down and across the whole eastern third of the U.S. We do not have as much of that by far here, but uh, occasionally, for example, you'll get ducting between here and San Diego, and where stations that are fairly modestly equipped and placed normally would not hear San Diego, they are getting good, strong signals from there. Another mechanism for VHF and VHF in particular is E-skip. The E layer of the ionosphere lies below the F layer, and of course, when just because signals are, it's lower, so the bounce, the hop is shorter than it would be, going all the way up to the F layer. Typical E-skip here in Southern California, one hop will get you into Denver, Pacific Northwest, Texas. Two hops gets you into Florida and points north from there. And that's mostly occurs on 6 meters, but we have had it occur a little higher than that. 10 meters, of course, will also experience that, but 6 meters E-skip is pretty common, and it really does not depend on the where we are in the sunspot cycle. Another technique used on higher HF and VHF and UHF is meteor scatter. Meteors, of course, these little grains of sand-sized things that come streaming into our atmosphere and burn up in the process from the friction, and they leave little ionized trails, and those ionized trails, just like the ionosphere itself, can refract signals and shoot them back down toward Earth. The typical maximum meteor scatter distance is around 1,200 miles, but I know there are stations that will use that in a contest. Um, I've made only one meteor scatter contact. That was many years ago, but I was in the Los Padres forest area of California, just north of Los Angeles, and on 2 meters CW, I worked a station in Montana, and we had to go back and forth a few times because these meteors can be very short in duration. Um, there may be only bits of information. You may only hear a few portion of a call sign, or you may get a nice long one. They called them a blue wizard that will hold for several seconds and enough to get a whole exchange. So, in order to take advantage of that, meteor scatter operators would usually schedule. They'd say, okay, the person on the easternmost person will transmit, say, in the first 30 seconds, and the westernmost will transmit in the second 30 seconds of each minute. And so you'd be listening, and they'd repeat the same chunk of exchange over and over, and hopefully among those little pings you get the whole piece of it, and then you go on to the next portion of the exchange, which you keep sending for 30 over and over for 30 seconds, and when they hear that, they know that you got the first part, and then everybody advances one part of the exchange, finishing up with RRR or 7-3. Moon bounce. uh, Moon bounce used to be really esoteric and limited to only a very few stations who had some monster equipment, and I'll show you an example of that. But it's become a lot more accessible to modest stations with the digital modes that have been developed just for that purpose. Uh, and are able to pick up signals considerably below the noise floor. We talked about line of sight. Here's basically the chart I was referring to. So if you're up at 6 feet, you got a roughly a 5 mile horizon, and it goes up basically kind of as the square root of your height. So if you can get up 400 feet, you got maybe a 25-mile horizon. If you can get up like Mount Fraser, where I operate a lot of contests, VHF and microwave contests, now you've got a horizon about 110 miles, and that does not include any of the enhancement for tropoducting or anything like that. So as I say, the troposphere can act like a waveguide. Now, I've also been in situations where that duct is too high. In fact, when Wayne went over to Hawaii to try and set some new records, uh, he started where the old ducts had been noticed and heard. There were beacons that old Paul KH6HME, now a silent key, had put up at the top of Mauna Loa at a television station. He was an operator there, and he put up these beacons on 2 meters and 440 and 1.2 gigs. And so people here would be listening for that beacon, and it was heard from time to time. But when Wayne went over there at his last successful trip at setting the records on several bands, uh, what he did was he set up a beacon on 220 at his home in Orange County in Southern California, and then was listening for it as he drove around. And he was up. He couldn't hear the beacon at all up near the top of Mauna Loa. And as he came down and down, he saw this layer of clouds, and he said, "Well, maybe that's where I need to be." And as he got into that layer of clouds, all of a sudden he heard that 220 beacon, and it got louder and louder, and he got the good spot, made the contacts with Greg, and he's got them all recorded. So you can be too high or you can be too low. In the case of the duct that crosses the Pacific, 10,000 is often too high, and you need to be maybe around 4 or 5,000 feet. And on this end, it's maybe between 500 and 1,200 feet. You can't get too high there. But fascinating. The E layer of the ionosphere, um, as I say, is basically it's very effective on 10 and 6 meters. You'll get a single hop uh, or double hop, and you can get. I've worked all 50 states. Some of that was when F2 was really good, but most of it has been on E-skip. From here, and that is also uh, effective on 10 meters. Several years ago, I was a part of a multi-operator group for the CQ Worldwide Phone Contest on Isle of Jersey, just off the French coast. We were Golf Japan 2 Alpha, I believe, and I was mainly on low band operator, but I went to help out on 10 meters. And I was getting this same it was just like 6 meters. The signal would be there for a few seconds and drop out, and you wait long enough and it'll pop back up. They call it sporadic E for a reason. Can be very sporadic. But over there, my single hop wasn't Texas, it was Israel. And the double hop was Kazakhstan, So it was just like operating 6 meters, but with a lot of DX on 10 meters. So, it's very interesting propagation, and you have to be patient because, as I say, a signal will be there. They'll come in from nothing to loud and clear, and then they're gone again. And one of the downsides of that is you may have several people using the calling frequency, say 50.125 on 6 meters, and all of a sudden the band opens and there are two competing people talking to folks, and well, I was here first. Usually people understand what the problem is, and they'll move up or down the band and continue. But it can be like a light switch turning on and off. Now, as I say, the F layer of the ionosphere also supports 6 meter signals when you have very high sunspots. This is my domestic grid square map. I got a bunch of stuff overseas, but these are the grid squares I have confirmed on 6 meters from home or from local mountaintops. And you can see you can reach pretty much anywhere under the right conditions. This area is kind of blank because it's mostly uninhabited desert. So there aren't many people there. And it's, the combination of catching somebody on the air plus having propagation is somewhat rare. I told you about moon bounce. This is a station that I visited when I was working in Houston. I went to see Dave Blakesheet, Whiskey 5 Uniform November, W5UN. And this is what he calls his MBA, his mighty big array. So you've got 4 Yagis on each of these poles. So that's 48 Yagis of, I think, around 14 elements each. This thing, it pivots on this center pole. And if you look down here in the corner, you'll see some wheels. He's got the back end of a pickup truck that is now having the gears driven by an electric motor. And so this thing runs around a track, around a circle, and it pivots. And that's how he does the azimuth adjustment. When I was there, he hadn't moved it for a while or used it for a while. So he asked me to go out and watch for interfering bushes that had grown up in his yard while he turned it. And he said, yeah, I've got to turn it. There's a repeater group 300 miles away, and I'm giving a talk tonight on 2 meters. So that's what he used for it. As I say, today, you don't need something quite this big. But Dave actually, even in back in the days when everything was analog, he would be able to work stations with just like 1 or 2 long Yagis and maybe 100-watt amplifier. When you're doing moon bounce, the gain is, the total gain is divided between the 2 stations. And if you got this much on one end, you don't need nearly as much on the other end. The stations don't have to be balanced or equivalent. But this thing was awesome to see. Now, microwaves. I've been doing this now for probably 15, 20 years. And it's an extension of the VHF contesting and roving that I used to do. But now I go up through all bands through 10 gigahertz. And I know several folks, we've actually used 22 gigahertz from time. And now we got folks on 47 and 110. So they keep stretching the envelope on those. Obviously, you have line of sight. You also have reflections off water towers and mountains and buildings, trees. And now, trees normally are the enemy of microwave. As the higher up you get, the more they act like they're basically, we call them green attenuators because of the moisture in them. But I know folks who have didn't have a good clear shot away from their home, so they pointed their 10 gig dish up to a palm tree and bounced the signal off the palm tree and managed to contact people. Airplane scatter is another thing you find. If there's an aircraft going between you and your target station, there'll be brief, almost like meteor scatter, there'll be brief periods of very strong reflection. And if you get that just right, you can make contacts with it. Rain clouds are another thing. Rain scatter is a very interesting feature. Now, because of course, rain clouds they don't have clean surfaces like an airplane or a water tank would, but they tend to scatter the signal and it becomes very mushy. You almost can't copy CW or even sideband. It's just, but that's where we go back to FM. Because FM is not so frequency critical. You can be, plus or minus a couple of kilohertz and you still hear the person fine. So we'll go to FM and it's almost like you're talking on a repeater. I've talked from Southern California here into Arizona on rain scatter, and it's a piece of cake. It's really amazing. So now guys are looking for, where there's some rain clouds, let's see if we can make something happen there. EME, of course, works here too. You need a lot more gain because the path loss is higher, but you can get that gain because dishes, big dishes can do, could really focus the signals. And I know there are European beacons on like 10 gigahertz moon bounce that have been copied here on the North America. Just to give you an example of what can be done, this is my confirmed grid squares from this star point here. That's up at around 8,000 feet in the Angeles Forest. This is on 10 gigahertz with a 24-inch dish and 2 watts and no preamp on the receive side. So up here, this is about 700 kilometers. So you see we've got several into Nevada, Arizona, up and down the coast. So it's really surprising. I tell people, this is basically the same range of frequencies as police radar, which maybe can go a mile or so. And this is the sort of distance we get. And that's none of that digital. This is all analog. This is mostly sideband with a little bit of CW, I think, for some of the farther reaches. The Nevada ones tend to be either Mel WA6JBD or Robin WA6CDR, both good CW ops and both good microwave guys. And so I've been roving up and down the San Joaquin Valley, and I've been able to work them in Nevada at every single stop using CW. So I think that's pretty impressive for a very, very modest station. Okay, let's talk about HF. HF is a totally different animal. Um, because the wavelengths are longer, they don't bounce off uh, buildings very well or water tanks or anything else. But when they hit the ionosphere, specifically the F layer, they can bend. And what you see here is an example of refraction. You've probably seen this plenty before. And what's happening is the light is going from one density medium to another density medium. And when it does, it refracts. So that's what we have. We think of it as a straight reflection, but it's really not. It's basically a bending. And how much it bends depends on the angle that you hit it at and the frequency. And there are a lot of other conditions that will change during the sunspot cycle, change during the year, and change between day and night. So HF, you've got surface or direct waves, and about the most you'll do there is about, somewhere between 40 and 80 miles, depending on the band. And those will be interrupted by terrain. Now, sky waves, on the other hand, can reach anywhere on Earth. How do they do that? Well, and where do they do that? That really depends on the angle of incidence. Where is what direction is being favored, and what is refracted? What's the ionosphere doing? Those of you who misspent your youth will recognize this sort of thing. If you hit the cushion at a very shallow angle, it's going to come back pretty close to where you started. If you hit it at a very shallow angle, it's going to come back quite a distance from where you started. And that's what we have on HF. So low angles can easily reach over 1,000 miles, and then they can take another hop and they can go all the way around the globe. I remember one contact I was having on 20 meters with a guy in the Great Lakes from Southern California here. And I was hearing the long path signal louder than the short signal. I was hearing him briefly, and then I heard him loud about a fraction of a second later. So it can go all the way around. So, but we do have this gap, this called the skip zone. And how big that skip zone is depends on the angle at which the radio signal is approaching the F layer of the ionosphere. If you have a higher angle, that skip zone is reduced. And if you get a really high angle, you've got almost no skip zone. This is what we talk about when we talk about NVIS, near vertical incidence skywave, used for regional communications. You want to spray RF, within a couple hundred miles of your station and everywhere in between. And so that high angle is what's going to do that for you. So there's something called a critical angle, and the critical angle varies with frequency. The higher the frequency, the lower the critical angle. The critical angle is where a signal hits, it will come back down. Um, and if you shoot it straight up, it may be too high. Uh, and above the critical angle, no refraction occurs. It just goes off into space. This is why you don't really have F2 propagation on, uh, 2 meters and on up. Uh, it's just it's not possible to have the signal come down because the critical frequency is for any angle is the highest one that will refract, and that critical frequency never gets as high as the upper VHF bands. They just keep going. So here's kind of an illustration of what happens on 10 meters. You hit it at a nice shallow angle, and it comes back. And so, when 10 is open, you get some really good DX around the world, but you're not going to use it for regional communication because those higher angles are just going to go off into space. Um, Now, 15 meters will support a little bit higher angle. The low ones will work, but also a little bit higher angle, so you can get in a little bit further. 20 meters, you've got more choices. It'll support low angle, intermediate angles, but seldom. Now, right now, there are parts of the world where 20 meters will actually come back down, but that's rare. Um, so the HF band, the higher HF bands, generally are good for working long distance, but they're not really that useful for local or regional communication. I did I kind of collecting states. I've got all states on 6 bands, but I don't have them on bands like 17 meters. This is what I've worked on 17 meters, and you can see I got most of the most of it, but those close-in states, I can't get. It's the angle it would take to have them come back down here is just pretty great. So I'd have to get some backscatter or some other unusual propagation to do that. Um, One year at a preparedness fair, I set up. It happened to be the weekend of the California QSO party, so there were lots of stations on looking to work California stations. So I just put up a little simple dipole on some fiberglass masts. Brought my K3 with a mic and a paddle and a deep cycle battery. And for the 3 hours of the event, I just worked people on 20 meters. And in that 3 hours, that's what I worked. And you can see we got all the way to the other end of the country. But again, where couldn't I get? Nevada, Utah, Arizona. Um, those angles were just too high to be supported by 20 meters. So let's look at 40 meters. During periods of low solar activity, um, they too generally will not support NVIS. Often you'll see that the critical frequency, it doesn't get up much higher than maybe 5 megahertz, which is why that 60-meter band could be particularly useful. Although, now they're talking about, with the World Radio Conference some years ago, they talked about cutting our power down to 10 watts or something. So that may take that out of play depending on what the FCC finally does. Um, but intermediate angles, it'll handle it. Now, during high solar activity, the critical frequency can get up to and above 7 megahertz. So now 40 meters could be a good band. Um, we have a California Office of Emergency Services, HFNet, where cities and counties around the state and other government agencies get on their ham stations on 40 meters, and when the critical frequency is up here, we can talk to them just fine around the state. 40 meters is great. Sunday mornings, some of the nets that all normally meet on 75 meters right now, because it's high spun sunspots in the summertime, they're meeting on 40 meters instead of 75. Now, 80 meters, most of the time, the critical frequency will be at or above 80 meters. When you're in very, very low solar activity, the bottom of the sunspot cycle, and at night, sometimes it will drop down to 1 or 2 megahertz, and then you may have trouble. Or if there's solar activity, solar disturbances, and that will be rare. Most of the time, 80 meters is a pretty good nighttime band, and even during the day, you'll be able to work regional stations. Now, the spoiler in a lot of this, you say, well, heck, 80 meters seems to have a, be below the critical frequency most of the time. Why don't we just use that all the time? Then we don't have to be running around figuring out what band to use. Well, the problem is the D layer, which is kind of the spoiler here. Uh, During daylight hours, the D layer, which is below the D and the sporadic E that we experienced on 6 meters, uh, it it basically it's the last to get energized from the sun and the first to dissipate at night. So it's really only active during daylight hours. But what it does is it absorbs RF, and it absorbs RF on low frequencies much better than it does at high frequencies. It's almost meaningless on 15 and 10 meters, but on 160 or 80 and sometimes even 40 meters, it can absorb a lot of signal. And so the signal has to go up through the D layer, gets attenuated, has to come back down through the D layer. So, um, that's why, you listen to your AM broadcast stations. If you're out in the, say driving out in the desert or you're camping somewhere where there's not, not an urban area, um, at nighttime, all daytime you're just going to hear local stations, but at nighttime the D layer disappears, and now the ionosphere can do its job of refracting those signals. And here in Southern California, get up in the deserts, we'll be hearing stations in Albuquerque and St. Louis and Denver and Salt Lake City and so on. Uh, and that's why, because the D layer that would inhibit those low frequency propagation kind of goes away. So what we have is an interplay between reliability and signal strength. As the frequency goes up toward the critical frequency, uh, the absorption is less, so the signals get stronger, but there's less reliable refraction. You're getting near the edge of when it's not going to refract anymore. It's just going to keep going into space. So your reliability goes down as you raise frequency. Uh, so as you go up in frequency, you get stronger and stronger signals until you reach the critical, what they call FOF2, and then often it disappears. So that's kind of a summary of the propagation. I did want to show you one other thing here, and that is, oops, where's my, I'm gonna have to go back and get it. There are a number of tools that are very useful on looking at particularly HF propagation. So let me see if I can bring one of those up. Hang on. Go to favorites. Just a minute here. All right, let me share this. This is that Australian site I was mentioning. And let me zoom in on it a little bit. Nope, it's not doing that. So here's a map. It's kind of centered on Australia, of course, because it's their government's program. But you can see here the areas in yellow, the critical frequency, that is the highest one that will come back down when it shoots up, is around 2 megahertz. And then it goes up from there. And you see right now we've got 10 or 11 megahertz out in the Central Pacific. For us right now in California, around 6 megahertz, and in most of the rest of the eastern part of the US, it's around 5 megahertz right now. So that would suggest that 40 meters might be a little high for a regional net at this time of day under these conditions, but 80 meters should be fine. And again, you'll see this change. This site is updated every 15 minutes, so you get pretty pretty good real-time information. Now, also, this is the ordinary wave, the FOF2. There's also an extraordinary wave, which is opposite polarization, a circular, it's a right hand, one's left hand. And the extraordinary wave could actually refract up maybe up to a megahertz higher. So you may be able to, cheat this map a little bit. The other site I wanted to show you is, let me get to that. Sure. Propagation. Spaceweather.com. This is a good one. Shows you what's going on. And then NOAA has a Space Weather Prediction Center. Dave just had that up too. Says he keeps it up regularly. So let's bring that up. Give me a moment.
They're not sharing.
Okay. Here we are. All right, now I think I can share this. Okay, here's the Space Weather Prediction Center site. And you have a variety of maps here. Let me see if this is the home one. Okay, so there's several maps. This particular one is showing the kind of the electron content, and as you might expect, the daytimes you can see a lot of activity, especially around the equator. At night times, it's died down considerably. And I'm not sure how to get to the Dave. Could you grab those graphs that?
Yeah, hit the dashboard up there where it says dashboard.
Up top?
Yeah,
There we go.
and then pick the radio communications dashboard from there. Radio, yeah.
There we go. Thank you. Okay, so this is kind of tracked for a couple of days in I think maybe 4-hour increments, and you can see back on the 17th we had very high geomagnetic activity, and that coincides with some solar events that took place and kind of wreaked havoc on a lot of the high bands, especially this map here shows auroral activity. This is great for people who want to watch the aurora, but for hams who are trying to get signal over the, say between North America and Europe, that can be a real barrier when that thing is very active. And you can see it quieted down, and then we had another peak just today. So that may signal, some more disruption later on. There are people who know a lot more about the interpretation of these numbers than I do, but you can do quite a deep dive into this, and there's nothing sure about HF propagation. It's all a matter of probabilities. Even the maximum usable frequency you may see on a chart or an analysis somewhere, it's an estimate, and it's going to vary. It can vary minute to minute, hour to hour, but it gives you it's the most probable, where you have maybe 90%, a 50% chance of successful transfer of a signal from point A to point B on a given path. If you want what's called the FOT frequency for optimum transmission, I think that's it's a lower frequency, and it's one where your reliability is up around 90% instead of 50%. So it's all probabilities, but this will give you an idea of what can be done. And again, we've got loads of people, especially now with the digital modes. You got people with very, very modest stations who are working countries all over the place on the HF bands right now, because propagation is fairly favorable on, say, 20 and 15, 17 meters. And you've got lots of folks who are working countries on FT8 and so on for the first time. I'm not a digital operator myself. I like to actually hear what I'm working, but there are those that like to dig a little deeper and use the digital tools that are available. So I think that's it. We can unhighlight and let's see if we got comments or questions.
Yeah, I might explain a little bit about the solar X-ray flux graph that was the top of those three graphs that was on the right side. If you get a peak there and it's on during the daylight side of the planet, that's what causes the blackouts. Sometimes you get an M class or an X class flare.
A flare.
Yes, and it can cause an HF blackout for 1 or 2 hours.
Right. The ionosphere is it's very delicate, actually. You could take the mass of the whole ionosphere and put it into a bed of a pickup truck. And so when you get these shock waves of either solar particles or whatever coming, it can disrupt that. It's not a mirror to start with, but certainly when it gets hit hard, that can mess things up. And we are normally protected by from the most harmful of the rays by a magnetic field around the Earth, just like the poles of around the poles of a magnet. But especially when you get big coronal mass ejections, it's like taking a rubber band and stretching it, and then it bounces back. And the folks who run power systems and so on worry about that, because what happens when you move a magnet across around a wire, or you move a wire in a magnetic field, current is induced, and that's what's caused some of these big blackouts, like up in Quebec a few decades ago, and other serious instances where that magnetic field was basically moving, and all those long wires on transmission lines would get current induced in them. There was a big one back in the 1800s that basically caused telegraph stations to have fires start in them because of the length of the wires and the strength of that magnetic field that was moving across them.
Gene's got his hand up.
Gene.
Yes, good evening, everybody. This is Gene from Glorious Clean, November 3 X-ray Uniform Sierra. Now, with the exception of trying to do moon, Earth bouncing around, does the moon play any other effect upon radio propagation away from the moon? I mean, not directed at the
Generally
moon.
not. No. The moon is not it's a reflecting body. It's not a hot body like the sun is. It's not emitting the high levels of energy that we're getting from the sun. So no, it wouldn't. Nor would any other satellites or anything. The sun is the big driver of what happens in the ionosphere.
All right, thank you very much.
Mm-hmm.
Okay,
Others?
anybody else out there? Oh, I can't believe there's that many bashful people. Where's Dan at?
No, most of them already know this stuff, I think.
Dan, WL7, COO, he is never without a question or an answer.
No, compared to Marty's knowledge, I'm nothing but questions. It's he kind of took me through a journey going back 25 years when I first got my amateur radio license, and RF was something more than just they issued you, so you could talk to headquarters, and it just amazed me about how sometimes you get really surprised and find out that 5 watts on an antenna that's put up entirely wrong. Well, a VHF will get you 3 or 4 states away. And other times on an HF, you got to struggle to be able to reliably talk to folks 3 or 4 states away.
Yeah.
And then the science about how, and I'm talking about sideband or FM,
Yeah.
but the science about digging out digital kind of put very different dimensions on all of that. And,
Very much. It expanded what anybody can do. But you mentioned being surprised. We were up doing the ARL VHF contest as a multi-op when you're up on I think we were up on Mount Pinos at the time, back when you could access it. And I was the 2-meter op. Sunday morning, I had a television sitting there on the generator box, and all of a sudden we see this Sunday morning preacher talking away, and he's got a little bit of an accent. And then I see the TV identifier, and it's in Texas. So I said, "Whoa, get on!" and pointed the beam over there, and we just started running Texas stations on 2-meter sideband for about half an hour. So we were shocked, but yeah, it happens.
And other things like when Arden brought well, I guess it really starts at 9 megahertz or gigahertz, excuse me.
Yeah.
And it goes up from there. But there's all kinds of interesting things about how they did the microwave long lines to increase the reliability and the distances they could go.
Yeah, and part of that reliability was picking frequencies that amateurs can use that are not part of the UNII, the public infrastructure, so that you don't have all that interference to deal with. They started actually on 2 gigs. We had a couple of channels that were down below the bottom of the UNII 2 gig band, and so they pushed they reprogrammed the routers and stuff to operate below, just below where they normally would. And then, of course, the 5 gig band, where we have lots of frequencies that are easily accessible, but not programmed into the ubiquity and other units like that. So they simply program them in, and so we have quite a few 5 gig mesh channels, and 5 gigs performs a lot like 10. And you saw the map I was able to do on 10. So, with some decent dishes, they can have some nice long haul, relatively interference-free paths.
And then, of course, there used to be the upper half of 3.4 gig, which, would give you different characteristics than 5 gig.
Yep. Until we lost
history
that.
though. And now it used to be a single brand of Wi-Fi routers that started Arden.
Yeah.
I forget the name, but they were just common. Huh?
Ubiquity.
No, Ubiquity was the newer, better stuff.
Well, actually, the Texas guys, they were using Linksys routers.
Yeah, there you go. Plain old
Linksys. The old Linksys routers that had memory in them. And but they never got past getting those couple of channels. They finally, it kind of ran out of whatever they could do with those units. And that's when Andre and the guys, in San Diego, decided to look to some different manufacturers. Okay, hey, thank you everybody, and good discussion. And these things are all recorded, so if you know some hams who are kind of just getting into particularly HF at any level of radio, encourage them to learn more about propagation and how they can take advantage of it, and the signals that are out there. Even listening, especially with some of the SD software-defined radio sites that are online. You can listen to stations in Europe. You can listen all over the place. Those SDRs, for anybody with a computer, even with no ham station, can be really educational in terms of what can be heard at any point in time. So with that, I'll say 7-3, everybody.